So thank you again. The last presentation of that session 4 is also remote by Ghinassi and collaborators about flow patterns and planform evolution styles in meander belts of the microtidal Venice lagoon. We have plenty. So up to then. Thanks.
Hi everyone, I'm going to show you results of our work in tidal meander bands of the Venice lagoon here in Italy. Why should be interested in tidal meandering channels? Actually, there are good reasons, both about modern channels, both in the deposits generated by these channels. In modern sectors, these channels are actually ubiquitous features of tidal landscape, and they are in charge for the exchange of water, sediment, and nutrients between closed lagoons, within the lagoons, and the open sea. They also offer different services. They are, for example, very important nursery sites for different organisms. And in the ancient record, they are important, both in terms of characterization of hydrocarbon reservoir, or if we go into more recent deposits, Holocene deposits, they actually control groundwater flow of the shallower aquifers in coastal areas because they, more or less, they form the skeleton of coastal sedimentary successions. So in this framework, aiming at going deeper in our knowledge about tidal meandering channels, what we are going to do with this study is to depict variety of different flow and platform patterns for evolution of these tidal bands. We are going to do this in the Venice lagoon, but just before going to the study sites, I will go quickly through the basics about tidal meanders and their morphodynamic evolution. What do we know about this? What about the classical models, classical facets models, for example? Actually, we know that they generally grow. We assume that they grow from almost straight channels, increasing their sinuosity through processes of outer bank erosion and inner bank deposition. Obviously, in tidal setting, we know that they are affected by opposing currents, but we also know that within tidal meander bands, these currents are mutually evasive. They are laterally offset, and the pathway followed by the maximum velocity flow during flat condition is not the same followed within the same band, is not the same followed during ebb conditions. What we are wondering here if these basic principles are enough, can actually describe all the possible variability of patterns we can find in modern tidal channels. So we are studying these channels in the Venice lagoon. No reason to spend time about an overview about the Venice lagoon because it's been described by several talks during this meeting. I want just highlight that is affected by a microtidal regime, and actually want to specify that this lagoon does not receive any relevant fluvial input. There are just 2 rivers entering the lagoon, but there's a spring rivers, so very low discharge both in terms of sediment and water. So the channels we are studying here are purely tidal, so these are blind tidal channels. Actually, we focused on 4 main cases, which are quite representative of the possible configurations we can find in the lagoon. These sites are located in the northernmost part of the Venice lagoon. That is actually the most naturally preserved area of the whole lagoon. Let's go quickly through these cases just to show you what we are going to study. So the first case is associated with what we call an expansional behavior. So this is really linked with the classical model. The band over the past decades simply increased its own sinuosity, developing classical point bar deposits. Something very different is associated with the second study case, where we are dealing with a cuspate band. Cuspate bands are typical of tidal realms, and they are characterized by an inner bank profile that is not convex, as generally we observe, for example, in fluvial point bars, in fluvial bands, but has this peculiar cuspate shape. In this study case, over the past decades, we observed that the channels, they tend to decrease their sinuosity, simply smoothing the apex of the cusp and accreting sediment along the outer bank, a behavior that is actually really unusual. We analyze as a third study case a translational band. which actually over the same time span, a few decades, simply moved, in this case southward, that means seaward, we will see, through erosion of part of its inner bank and deposition along the other side. So a very, would say, asymmetric behavior. The last case is associated again with the Caspate band, but this band over the past 70 years didn't show any significant change in planform. So this case is a very stable form. What have we done in these bands, in these sites? We measure flow velocity, ADSP measurements during spin condition, both for flood and ebb flows, and recovery sedimentary cores. Okay, just especially to verify specific vertical grain size trend within the study deposits. Just few words about the study deposits. Channel lags, they are present in all the study cases, of course. They occupy mainly the deepest part of the channel. They consist of medium to fine sand, and they are very rich in shells, shell debris, and mudclasts derived from collapses of the outer bank zones. If we look at the point bar deposits, actually at the deposits associated with these channels, in grain size they are slightly finer than channel lag deposits. They are characterized by a pervasive planar lamination that dips toward the channel at about 10 to 25 degrees. Let's have a look now at the different study cases. So let's start with the easiest, let's say, the classical one, expansional band. At this site we measure velocities up to 20 centimeters per second. It's nice to see that actually the pathway for these maximum velocities is mutually evasive as described by the classical models. So in the flood stage you can clearly see that the maximum velocity here is close to the inner bank. At the apex zone shift toward the outer bank and then move along the outer bank. Opposite pathway for the ebb stage, close to the bar in this zone and then shifts against the outer bank and goes on along the outer bank. So mutually evasive currents as predicted by classical models, and is also pretty evident here that we don't have any clear flow separation or development of recirculation zones. I want to highlight again this point about the mutually evasive currents, stressing the point that the maximum velocity zones are always measured both in the flood stage and ebb stage close to the inner bank, close to the point bar. This is quite interesting because if we recover sedimentary cores from the point bar, from the associated point bar, we can clearly see that in both cases, in both the cores, we have the coarser deposits which are accumulated close to the inner bank. This is quite unusual if we want to try and make a comparison with fluvial bands, for example, where you can expect, especially in the downstream side of a fluvial band, we could expect a classical fining upward grain size trend. The upstream side of a fluvial band can lack this classical fining upward grain size trend simply because the highest velocity impinges against the point bar in that zone and carry over the bar the coarser deposits. Here we have actually something that is quite similar to this process. The highest flow velocity is always sited close to the bar, and this prevents the formation of a classical fining upward grain size trend. This is quite peculiar. If we shift to the next case and we analyze the Caspate straightening channel, is slightly deeper than the previous one, 3 meters against 2 meters. And in this case, we can clearly see that the flow velocity is similar, more or less 20 centimeters per second. Also in this case, we don't see clear flow separation processes. These are very localized. And also in this case, we can clearly observe the offset of the two of flood and ebb currents. We can clearly see that the area that is affected by flood flow here, the maximum velocity zone, is actually not the same when we consider the ebb flow. So also in this case, the currents are offsets laterally. What is quite interesting here, as I told you, is that over the past decades, actually the point bar, if present, was actually eroded, and most of the sediment was accumulated along the outer bank. If we look at the sediments, they are generally muddy. They consist of mud to fine sand, but all the cores show a quite clear fining upward grain size trend. This actually reflects the progressive shift of the maximum velocity zone from the outer bank toward the inner bank. What about the translational band? Actually similar in size as the previous one, 3 meters deep. In this side we measure the highest velocities, but actually this side is quite different from the previous one, especially in terms of development of flow separation zones. We can clearly see, for example, here close to the outer bank, that there are zones which actually are affected by the same flow both during the ebb stage and the flood stage. This is associated with development of recirculation zone, which can locally prevent a specific area to experience opposite flows. And this is quite interesting because actually even if we are confined within a channel, the same zone experience always a kind of unidirectional current. It's also very interesting to note here that tidal asymmetry is quite marked because we can clearly see that the same side experience opposite velocities with a quite remarkable difference. Right? The velocity pattern is also quite interesting in terms of planform evolution of the band. We can clearly see that the maximum velocities here during the ebb stage, they cause erosion of this bank, this part, the side of the inner bank, and we have of course deposition along the other side, where actually we have the maximum flood velocities. If we consider the grain size of the deposits associated with this band, we clearly see that actually the presence of strong flood currents along the seaward side of the band is clearly documented by the presence of sandy deposits on the point bar top. So this is quite counterintuitive. We have ebb dominance in terms of planform evolution because we have erosion on one side where ebb currents are directed against the bar, and the position on the opposite side. But the position is mainly controlled, especially in terms of grain size, by the flood currents. The last point is the last study case is a stable cuspate band. It's a much shallower channel, so we didn't manage to run ADCP measurements. We managed just to have an idea about flow velocity during a tidal cycle using current meters. We have the specific site flow velocity that is maximum during ebb, 40 centimeters per second, and during flood we measure the maximum of 30 centimeters per second. What is helping us here to define processes within a band is actually the shape of the band itself and actually also the morphology of the channel. If we compare the plane view expression of this band with the channel morphology, we can clearly see that flood currents here, red line, are able to scour a secondary channel that sides the inner bank of the measure one. This is what is called a barb channel, and between the measured pathway of the flood current and the measured pathway of the ebb current, we have a localized accumulation that is a barb. Actually, in this setting, this peculiar flow configuration prevents the channel to migrate lateral because it actually prevents accumulation of point bar deposits. The only accumulation here is associated with a barb body that is actually very, very thin because it's just 20 to 30 centimeters thick, and just below the barb coring we can find saltmarsh deposits with nicely preserved roots. So this peculiar flow pattern here prevents actually the mobility of the channel because it hinders the accretion of the bar itself. So we actually analyze a pretty wide spectrum of different configurations. So we can clearly state that planform transformation styles, which we can find in lagoonal environments, can clearly differ from classical expansional models. In this framework, also the asymmetry of tidal current has a key role in shaping behavior of different type of bands, planform style evolution. But it's also intriguing to note that in some cases this peculiar flow pattern can deeply impact on grain size distribution within deposits related within these bands. And this means that actually the grain size distribution can carry the signature of tidal process within these deposits. And that's all, and thank you for listening.
Thank you for that nice presentation. Let's go to the question. Yes, Jasper?
Do you regard your measured velocities as having any influence on the morphodynamics of your system?
To be honest, I guess just a few words. I'll do my best to provide an answer to this. So if I properly got the point, the flow velocity is not enough to move sand. And actually, this is true. We should just consider 2 points. That most of the bars are made of sediments that are finer than sand, very fine sand to silt. And as Davide showed this morning, actually most of the load of the sediment load that is building up these bars comes from suspension. This is the first point we should consider. The other point that we carried out this measurement during spring tides, but not the highest tides, not the largest tides, because we did some measurements during summertime, and the highest tides are generally during autumn here. So maybe the effective flow velocity could be even higher than what we measured. These are the 2 points that I like. I don't know if I properly answered the question.
Yes, as I see it, your system is built on morphodynamics, which is several numbers higher than you are measuring, and that's of course fine, but perhaps you could comment on when that happens. Probably it is under storm surge. Have you any measurements from a storm surge?
I'll let me know. As I told you, that we didn't take measure during exceptional, let's say, events.
Because you need that also to erode your banks.
Okay.
Okay.
Other questions? Yes, Yuntik?
Hi, General, it's Ghinassi.
Hi.
Okay, I would like to know the general characteristics of the tidal asymmetry in the Venice Lagoon. If there's flood dominant areas, do you find any candidate for upstream translating point bar? If you don't have any, do you have an idea why there's no upstream translating point bar?
Okay, thank you. That's a good question. Let me quickly think. The translating bars we analyzed, in detail at least, are moving always toward the sea. But actually, this would be, okay, the whole system is dominated, we know that. So air currents are dominant, so this could reasonably explain a seaward translation of all these bars. This does not exclude that we could get locally some landward migrating bars because of local dominance of currents that could be associated with a complex circulation within the tidal network within the lagoon.
Okay, one last question.
My question is for the barb deposits, barb bar. If you have some comment about their preservation potential or lack thereof in the rock record, if you could have.
Very interesting. Actually, if you look at the tidal channels from Google Earth, we see many of these bars. When we go in the rock record, they are really purely documented. I remember one paper by Chris Fielding in Permian deposits in Australia. identified something that he called bar. And we think that we got something similar in the transformation in Spain, the unit Marta Cosma described this morning. Actually, it could be a little bit tricky to identify them because if they are sited on top of a point bar, they could be easily misunderstood and confused as scroll bars. Morphologically, they are just mounds. And in other cases, the easiest way to identify them would be actually to be sure in a cross-section transverse to the channel axis. You could see that the main channel that discovers much deeper than another side channel, the bar channel. I would think that they could imitate a kind of mid-channel bar in some cases. But actually, as far as I know, they are not so commonly documented. So a lot of work to do on that.
Okay, no more questions? So I have to thank you so much, Massimiliano, in spite of the technical problems we had. It was very sad. So it's time to close the session. Thanks to all who have attended it. I hope you enjoyed it as much as I did. In fact, through diversity, we see that the tidal systems are well studied now and things are going on. Thank you.